Hi, I'm Neha Makhija, and this is joint work with Wolfgang Gattenbauer that was presented at PODS 2024. Someone came up to me yesterday and said they have a long Boolean formula, something that was very complicated and looked like this, and they didn't know what to do with it or how to process it. And I said, oh, why don't you factorize it? This expression is simpler, it's equivalent, and I computed it efficiently. This surprised them, and they asked, oh, how did you get this factorized formula so efficiently? Because they knew about the result from 2011 that said the minimum equivalent expression problem is in the second polynomial hierarchy, so they were unsure how I solved this general problem. And I said, oh, I didn't solve the general problem. I found some extra information. I knew that the Boolean formula that they showed me came from the output of a query, and it was the provenance, and that's the information that I used to factorize it efficiently. So then they went, aha, I know what result you used. You computed a read once expression, which means that the resultant factorization had no repeated literal. And if the smallest factorization does have this property that can be represented without repeated literals, you can find the simply time. But I said, no, the formula that I showed you, the factorized version, does indeed repeat some literals. It's not read once, so this is not the result that could have been used. And then they asked me, well, did you use results from factorized databases that give you the asymptotically optimal factorization? So that could be another factorization that's smaller, but it won't be asymptotically smaller. And I said, no, the factorization that I showed you is actually instance optimal. There is no smaller formula at all. And the reason we can do this is that in our paper, we have new tractable cases for some provenance formulas. Let me give you a quick rundown of what I mean by a provenance formula. Let's assume we have as input some tables or relations, RNS, that have some columns, attributes, and some rows or tuples. Each tuple has a provenance token, here R1, R2, S1, S2, that represent each input row. Then we run some query here in Datalog and or in SQL, which basically joins the RNS table and all values that have the same Y. And here all tuples join with each other, and we get 4 output rows, each of which is denoted by some combination of tuples that constitute the output row. And here then we can get the provenance expression, which is a disjunction of all the output rows. And I also show you the minimal factorization, which is just read once and has no repeated literals. We can see that the provenance formula has some nice properties. It's k-partite, it's a monotone Boolean formula, and it follows joint dependencies. So if we know that certain tuples join with other, from that we can often infer the presence of other joint tuples as well. And now the question is, can we leverage these nice properties to make the factorization problem easier? Turns out the answer is yes, and I will talk about this a bit more in this presentation. But before that, let me highlight some restrictions. We only look at self-join free conjunctive queries. The provenance of these has the nice property being k-partite. We also say that the provenance DNF, disjunctive normal form, is given to us as input. And we're finding the minimum formula representation, not circuit representation, which is also separately studied problem. Before I dive into the results of this paper and how they were achieved, I want to say a quick few words about why we should study this problem. So the first motivation to study this problem is a purely theoretical curiosity. It's a very simple sounding problem, one you might explain to your high school algebra class, but yet there are many open mysteries. So it has led to very surprising complexity results in the past. The minimal equivalent expression of problem was studied in 1972 and initially presented there. And it was only shown to be NP hard, but not NP complete, and the proof of the exact complexity of NP completeness was missing. And the reason this was so was because only in 2011 it was shown that it was in the second polynomial hierarchy, which was an unexpected result. Something else that is interesting is that there are few known tractable cases. So read once, like I mentioned, is one, read polarity once is another. But other than that, there aren't too many known tractable cases where you can find the smallest factorization in p-time. And so finding new tractable cases is interesting and useful. The other motivation, surprisingly, comes from probabilistic inference. A dichotomy for self-join free conjunctive queries is known. If you have a hierarchical query, then probabilistic inference is in p-time. Interestingly, hierarchical queries are precisely those that have read-once provenance. And this is an interesting connection. This connection was extended by the observation that if you have a read-once provenance, no matter the query, so if you just focus on the data but not just the query, then you can recover more cases where probabilistic inference is easy, whenever the data has a read-once provenance. The approaches on the top row work for whenever you have read-once provenance or a p-time case for probabilistic inference. But what if you wanted to do approximate probabilistic inference and recover these p-time cases automatically? This generalization was studied in 2015, and they recover hierarchical queries as a special case. In our paper, we show that finding the minimal factorization can recover p-time cases based on the data as well, even if the query is hard in general, and is a complete solution. So you can find approximations always and p-time cases whenever possible. We studied this experimentally and found that indeed the approximate probabilistic inference generated from the minimal factorization of the provenance is a pretty good approximation to the exact solution. So here, the blue star denotes the approximate solution from minimal factorization, and the yellow circle is the exact probabilistic inference. So it's a pretty close match. Now that we have some motivation for this problem, I want to present some key results and the ideas behind them. How do we actually compute the minimal factorization given a provenance DNF? The first step, or the first ingredient in this process, is discovering some connections between factorizations and minimal query plans. The first intuition is that evaluating the input with different query plans actually corresponds to different provenance factorizations in the output. Let me show you some examples. So here we have three input tables, R, S, and T, and they join together to form a chain. And we have the outputs also represented in a graph below. So each path is an output below. All right, so now let's evaluate it with some query plan. Let's say you just join all the tables together and then project everything. This corresponds exactly to the DNF factorization with length 15 and every literal repeated in each DNF. Now, we can also use a smarter plan and join the S and T tuples first. This corresponds to essentially factoring out the R, and we get a smaller factorization. We can do this symmetric query plan and join S and R first, and this corresponds to factoring out the T tuples now, and we also get a smaller factorization. Our second insight was the following. Why limit ourselves to just one query plan to find the minimal factorization? We can use multiple, a combination. So continuing on with the same example, we now take both of the query plans that we were now considering, first joining on S and T or first joining on S and R. And we can combine them to get a factorization that is even smaller than the ones we had before. So now length 12 instead of 13. This is great, and indeed this smallest factorization, but not read-once. But just knowing the combination of query plans is not enough. We also need to know how to assign the data to different query plans. So if I use the same combination, I can still get something that is long and unoptimal. So we need to assign query plans to DNF terms. And this is how we change our factorization problem to essentially an assignment problem, where we're now assigning query plans to DNF terms in the provenance formula. So what we show in the paper is that essentially this assignment problem can always recover the minimal factorization for any self-join free conjunctive query provenance formula. And the way we show this is through several intermediate constructions. It's a constructive proof that the details of which are not in the doc but are very much in the paper. We show something more. We show that you don't need to look at all possible query plans to assign, but just a subset called the minimal ones. And the notion of this minimal query plans actually comes from probabilistic inference and is studied in a paper there. And we adopt this concept and show that these minimal query plans are enough to find the minimal factorization. With the previous series of insights, we've sort of converted our factorization problem to an assignment of query plans problem. But we still need to solve it. And for this, we show two algorithms that are unified. And I will explain what this means. The first algorithm is an integer linear program. Integer linear programs can be hard in general, but there are some cases that can be solved in time. The second algorithm is a flow algorithm, and these can always be solved in p-time, but sometimes return the approximate solution and sometimes the exact one. We show that both of these problems are unified for minimal factorization, and what this means is that all known tractable cases can be solved in p-time exactly by our formulations of the integer linear program and the flow algorithm. I will first give you an intuition of our integer linear program formulation. So like we've said, our factorization problem can be reduced to a query assignment problem. And for this, we add a constraint. For each DNF term in the provenance, we pick at least one query plan. And the constraint looks something like this. So for each DNF term, you'd have a constraint that say, hey, either pick query plan 1 or query plan 2, and you must select at least one of the different query plans. We also have a second constraint called a prefix constraint, which says that, hey, if a query plan is picked, all the prefixes must be picked as well. And the constraint looks something like this. If a certain query plan is picked, it has value 1, then the prefix of that query plan is also picked and must have value 1. The goal of the chosen assignment is to maximize the repeated use of prefixes, thereby factoring more things together intuitively. So the objective is to essentially reduce the cost of all the prefixes that we've chosen, and looks something like this, where cost is defined based on the different types of prefixes, and we simply sum all of them together. This is essentially all the ingredients needed for an ILP, the two types of constraint and the cost function. And we showed then that this ILP formulation actually has this identical objective value as a relaxation, the LP relaxation, which can be computed in p-time. And so we can use this ILP formulation to automatically recover all tractable cases of minimal factorization in p-time. The second sort of unified algorithm is the flow algorithm, which we show is always exact now for the tractable cases. The flow algorithm is formulated as a min cut or minimal cut problem, where the minimal cut is the minimum cost of nodes whose removal disconnects the source and the target. So in this graph, cutting the two nodes on the left with cost 1 and 2 would indeed disconnect the source and the target, and these are the minimum cost subset of nodes that would disconnect the source and target. Now we can formulate our factorization problems in min-cut problems. So first, let's take the query plan constraint and see how that would fit in as a min-cut. Well, our constraint was to pick at least one query plan, so we simply connect them in series between the source and the target, and at least one of the query plans must be cut to disconnect the source and target. This corresponds exactly to the constraint that said at least one of the query plans must be chosen to fulfill the constraint. And here you would pick at least one of these. Next, we must also model the prefix constraint that says that if a query plan is chosen, so are its prefixes. And this can be modeled by connecting the prefixes in parallel with the corresponding query plans. So now, if a query plan is cut, it also makes sense to cut the prefix. And we can also add in the same cost that we use in the ILP to the min-cut formulation as well. So now we've taken all the constraints and objective of the ILP and modeled it as a min-cut. How was this possible, since min-cut is a problem that can be solved in p-time, but ILP is not? Well, we have modeled all the constraints of the ILP, but we may have created some extra constraints as well by the interaction of these different constraints and paths, thereby causing an over-approximation. Moreover, ordering the nodes differently can actually lead to different results, and this is not something we take into account. However, we are able to show again that for all tractable cases of minimal factorization, there is some ordering of nodes that always leads to the fact that the minimum cut of the produced graph is equal to the minimal factorization. And we can find this ordering and use it to find the minimal factorization in p-time. I have been mentioning the tractable cases or the p-time cases of minimal factorization. I want to show you our results about that now. Before I give you a general overview of the tractable cases, I just want to give you some examples of complexity of this problem. So here is a query which has 3 minimal query plans, so only 3 plans need to be assigned in the integer linear program. It contains a cycle. Here's another query which also has 3 minimal query plans, also contains a cycle. Turns out you can solve minimal factorization for only one of these in p-time. This is completely non-obvious, and this example is just to show that the complexity of minimal factorization is non-obvious. What are the queries for which minimal factorization is tractable? The first class is well known, and I have discussed it already. This is the class of hierarchical queries, and turns out this is also the same as queries that have one minimal query plan. So for this, minfact can be found in p-time. This was well known. We show that even if you have two minimal query plans, then you can still find the minimal factorization in p-time. So this is a new additional class of tractable queries. And the proof is based on total unimodularity of the ILP constraint matrix, and this is a concept from linear optimization. Interestingly, we show that even if you have more than 3 minimal query plans, you can still find queries that are p-time. So for example, the 4-chain query. But in general, this class is open, and there are some easy queries and hard queries, and we don't know what the dichotomy criteria is. The proof for the queries that we show are p-time in this class are complicated and case-wise proofs that are hard to analyze and prove. And so we might need new proof techniques to make progress in this. On the flip side, for what queries is this problem known to be NP-complete? It was not known, but we show that if a query has an active triad, which is a notion also used in the resilience problem, which we define in the paper, then turns out the minimal factorization problem is indeed NP-complete. Additionally, we show a different criteria, which is also defined in the paper, for which the problem is also NP-complete. What these results lead us to is a complexity sandwich. So we know that the minimal factorization problem has strictly more tractable cases than probabilistic inference, since more than the hierarchical queries are in p-time, and strictly less tractable cases than resilience, since it's hard for all the queries for which resilience is hard, as well as some more. So I've spoken about the connection between factorizations and assignments of query plans. I've shown unified algorithms, as well as new tractability results. So let me talk now about what's next. The first, most obvious open question is to complete the complexity dichotomy and find out for which queries is the minimal factorization problem tractable. And we conjecture here that all path queries, so 5-chain, 6-chain, and beyond, are indeed tractable. Why can't we prove it yet? So the matrices go beyond the existing tractability criteria that is known for integer linear programs, like total unimodularity or balanced matrices. And we might need more insights from linear optimization or yet to be discovered insights that might help prove this. The other type of proof, which is based on flow graphs, is a complicated case-by-case analysis. So we might need some way to automate this or make this process faster to discover more proofs there. The second open challenge is finding complexity results in dealing with queries with self-joins, bag semantics. What if you have a Boolean formula that is non-provenance? In what cases can our techniques be extended and applied? What are the main takeaways? So the things that I'm most excited about is that we have new tractable cases for factorization, something that is not very common to see. We also show unified algorithms. So this is a new perspective where you have a single algorithm for all cases, but you automatically optimal for all tractable cases. So you don't have different algorithms for easy and hard cases and different types of easy cases. The third insight is that there are many deep connections between probabilistic inferences, dissociations, minimal query plans, and factorizations that would be great to explore more. You can check here for more resources and details of the paper, and also a related paper on resilience that uses unified algorithms as well. And please get in touch if you have any more questions. Thank you.